Welcome to the next session of Embedded Systems. The topic is memory organization. It will be presented by myself, Dr. K. Kanimali, Professor Tripoli. In today's class of memory organization, we will be discussing about the types of memory which is available inside the embedded system and its block diagram, followed by the various addressing modes. To start with the memory organization, a table has been shown which indicates the available memory in a PIC microcontroller. In case of device, it is PIC 10F87 or 88, and the program flash memory is 4K, data memory is 368 by 8, and data EEPROM is 256 by 8. In case of PIC 16F84, the program flash memory is 1K by 14 and data memory is 128 by 8. The data EEPROM is 64 by 8. PIC 16F84 has two separate memory blocks for data and for program. The EEPROM memory with the general purpose register and special function registers in RAM memory make up the data block, while flash memory makes up the program block. The program memory has been carried out in flash technology. The size of program memory is 1024 locations with 14 bits width, and 4 are reserved for reset and interrupt vector. In case of data memory, it consists of EEPROM and RAM memories. The EEPROM memory consists of 64 8-bit locations. The EEPROM is not directly addressable, but it is accessed indirectly. The EEPROM ADR and the EEPROM data registers. EEPROM memory usually serves for storing important parameters. The RAM memory for data occupies space on a memory map from the location 0x0C to 0x4F, which comes to 68 locations, general purpose registers. The special function registers take up to 12 locations in a bank of port 0 and port 1. Okay, next we can see the block diagram of this memory organization. To start with, the program memory and the various locations are shown. So the program memory which is shown here, it starts from 000H to 004H. So from this, the program address is created. That address bus is connected to the stack level 1 to 8, and it will be connected to the program counter. We have got a status register in which we can set the status flags as shown. So this status register and the address register will be connected to the general purpose register. So the general purpose register's address starts from 00H to 0CH. It is connected to the data bus, connected to the address bus, and different addresses which are being used are shown. It is shown for both bank 0 and bank 1. The different locations of address for a microcontroller PIC 16F84 is presented as an example. The same scheme will be followed for other microcontrollers also. The number of address bus and data bus may vary depending upon the memory which is being consumed. If it is designed for more memory, more number of address bus and data bus will be allocated. Next one is the memory banks. The memory map is divided into with two areas called banks, bank 0 and bank 1. Selecting one of the bank is done via RP0 in the status bus. So the status register, it has got 8 bits starting with IRP, RP1, RP0, T0, PD, Z, DC and C. For example, if we use the status RP0, here the instruction BCF clears the bit RP0 in status register. If we use the example BSF status RP0, the instruction BSF, it sets the bit RP0 in status register, and thus it sets the bank 1. So likewise we can select bank 0 or bank 1 while writing the program. In case of bank 0 micro, the instruction is BCF status RP0. If it is bank 1 micro, it is BSF status RP0. Next is the stack register. In case of PIC 16F84 microcontroller, it has a 13-bit stack register with 8 stack levels. Its basic role is to keep the value of the program counter after a jump from the main program to an address of a subprogram. In order for the program to know how back the program is being counted and how the program is being executed, and when it goes to the address of a subprogram where it is started from, it has to return the value of program counter from a stack. When moving from a program to a subprogram, the program counter is being pushed on to a stack. When executing instructions such as return LW or return FIE, which were executed at the end of a subprogram, the program counter was taken from a stack so that a program could continue where it was stopped before it was interrupted. These operations of placing on and taking off from a program counter stack are called push and pop. Next is the data memory. Data memory is partitioned into two areas: special function register area and general purpose register area. The GPR area allows greater than 116 bytes of GPRAM. The data memory can be accessed either directly using the absolute address of each register file or indirectly through the file select register. So the block diagram for the register file map is shown. So it includes indirect addressing mode for 68 general purpose registers and indirect addressing modes for mapped accessed in bank 0. So the various options available are option register, program counter register, status flag, special function register, port A, port B, EE data, EE ADR, PCL ATH, INT con, and EE con 1 and 2. All these functions or flags are available both for bank 0 and bank 1. Next one is the addressing mode. We will be discussing two types of addressing mode: direct addressing mode and indirect addressing mode. The RAM memory locations can be accessed either directly or indirectly. In case of direct addressing, it is done through a 9-bit address. So example program is BSF status RP0. So here bank 1 will be fetched. Move LW 0xFF, that is the value 0xFF will be moved to the register F. Move WF TRISA. So TRISA is a register which is taken from the instruction MOVWF. So here the address will be fetched. Next is indirect addressing mode. Indirect addressing mode, unlike the direct addressing mode, it does not take an address from an instruction but derives it from the instruction register bank, bit of the status and FSR registers. The address location is addressed via an instruction called as INDF register, which is in fact holds the address indicated by the FSR. The next it is the various memory management techniques which are used. The various memory management techniques are fixed block allocation, dynamic block allocation, dynamic page allocation, dynamic data memory allocation, dynamic address reallocation, multiprocessor memory allocation, memory protection to OS functions, and memory protection among the tasks. In case of fixed block allocation, the memory address space is divided into blocks with process of small address space getting a lesser number of blocks and process of big address space getting a large number of blocks. In dynamic block allocation, the memory manager allocates variable size blocks dynamically allocated from a free list of memory block description table. In dynamic page allocation, the memory has fixed size blocks called pages, and memory management unit allocates the pages dynamically with a page desirable table. In dynamic data memory allocation, the manager allocates the memory dynamically for different data structures like nodes of a list, queues, and stack. In dynamic address reallocation, the manager dynamically allocates the address bound to the relative address. It adds the relative address to the available address in the address relocation register. This is also called the runtime dynamic addressing binding. In multiprocessor memory allocation, it adopts the tight coupling or loose coupling between two or more processors. Finally, in memory protection among the tasks, read and write operations are not permitted to a particular memory space allocated to another task. The last topic will be in-circuit emulator. In case of in-circuit emulator, it is the use of hardware device of the in-circuit emulator and to debug the software of an embedded system. It operates using the processor with the help of an additional ability to support the debugging operations as well as to carry out the functions of a system. In-circuit emulator is a computer chip that is used to emulate a microprocessor, that it mimics the functions of a microprocessor, so the system software can be tested by the developer. It is called as a testing platform. It allows the programmer to check the program which has been written before embedding it into an embedded system. The in-circuit emulator gives the option of debugging before being marketing into a final stage. So the block diagram is shown. In-circuit emulator, it has got a target system. The emulator probe will be connected to the in-circuit emulator and finally connected to the workstation. So the working principle is the programmer uses the emulator to load the programs into an embedded system, run them, step through them slowly and view the change data used by the system software. It imitates the central processing unit of an embedded system, so it is checking before it is being available to the marketing stage. So it will be checked in the laboratory level itself. The house of a microchip offers in-circuit emulators are of three types: MPLAB ICE 4000, Real In-Circuit Emulator, and MPLAB In-Circuit Emulator 2000 version. So in today's class, we have seen the memory mapping, memory allocation methods, and in-circuit emulator. Thank you, students.